Hello and welcome everyone to our 18th PyData meetup. My name is Torian Dyer and I'll be your host for this meetup. And today's topic is going to be training session-based recommender models with transformers by Gabriel de Souza, Senior Research Scientist at NVIDIA, and Ronay, Senior Data Scientist at NVIDIA. And as always, before we begin, we have to go through our PyData code of conduct. So please be kind to others. Do not insult or put down others. Behave professionally. Remember that harassment and sexist, racist, or exclusionary jokes and language are not appropriate for PyData. All communication should be appropriate for a professional audience, including people of many backgrounds. Sexual language and imagery is not appropriate. PyData is dedicated to providing a harassment-free event experience for everyone, regardless of gender, sexual orientation, gender identity and expression, disability, physical appearance, body size, race, or religion. We do not tolerate harassment of participants in any form. So we want to thank you all for making this a welcoming, friendly, and educational place. And once again, we'd like to introduce Gabriel and Ronay as they tell us and teach us about training session-based recommender models with transformers. Take it away.
Awesome. So yeah, thanks for having me, Torian, for inviting us, me and Ronay for this talk. It's my first talk targeted for Trinidad and Tobago folks, so I'm really excited to be with you today. And yeah, can you see my screen, by the way?
Yes.
Okay, perfect. So let's get started. So yeah, as Torian said, today we're going to talk about training session-based recommendation with transformers. And yeah, sorry for my voice. I've got a sore throat, but yeah, I think we can make it. This is me and Ronay. We both work at NVIDIA, and we work in the Merlin team, which is focused in recommender systems, right? So you might think, why NVIDIA is talking about recommender system, and hopefully in the end of this presentation, you understand the type of software content we are delivering to this space. So NVIDIA is not only about GPUs, but also about providing libraries which are domain specific, and we have worked specifically in the last 2 years focused in recommender systems in the Merlin team. So this presentation will be split in two sections. In the first section, I'm going to provide an introduction on sequential and session-based recommendation, and also introduce the Transformers4Rec library. It's more like a conceptual part. And then later we're going to have Ronay presenting a short demo highlighting how Transformers4Rec, which is an open source library, can be used for this task. So yeah, let's get started. So before jumping into sequential session-based recommendation, let's talk a bit about recommender systems, right? You might not be aware of, but most of the online content you interact with is powered by recommender systems. So you might think in the digital content you consume from Netflix and YouTube, or whether you're browsing on Amazon or your preferred e-commerce, when you're using any social media platform, or when you're just browsing and get some recommendation, there's an engine there, a machine learning model, which is trying to learn what are your preferences about and try to recommend relevant content for you, right? So this is both good for users because they, in theory, can get access to from a large catalog. You can have your search space reduced and hopefully get some relevant recommendation. And also for the ones that provide those items, there are a few items that are very popular. For example, if you go to Amazon, you might see that Kindle is a very popular product there, but there might be some niche products that will be purchased by person that have some specific preference. And the recommender systems really is about trying to leverage that long tail and recommend those niche items to the people that might want them. So how does a typical recommender algorithm work? Here we have an example of a matrix where we have users and items. And we have some known ratings from some users. For example, Ted, which is the first user, he has interacted with item B and D. It might be a movie, for example, and he provided 4 stars for item B and 3 stars for item 3, for item D, sorry. And a typical machine learning model for this task is try to complete this matrix so that basically it tries to learn some factors or some vectors that represent that user and some factors that represent the items. The dimension should be the same so that when you multiply the user and the transposed item matrix, you get a full matrix, like a dense matrix with scores predicted for all positions here, right? And the idea is that you should recommend to Ted items that scored higher here in the predicted matrix, ignoring the items that he has interacted before. So this is the typical approach called matrix factorization, where users and items are decomposed in latent factors, and then we try to reconstruct this matrix. We train with the known ratings and try to predict for all items so that we can provide recommendations of other items for those users. But this assumes static user preference, right? Let's say the user has changed his preference around movies or around some hobby. This type of model doesn't account for how recent is that preference. So that's a limitation here. But user's preference also change over time. So for example, let's say a user has read books or online content on gardening for like a decade. And then after he starts like more on cooking, and more recently he starts doing some sports like cycling. So in this case, what should we recommend to the user? Gardening stuff, cooking, books, or cycling posts? So definitely we should put more weight in the recent user activities. So that's where sequential recommendation comes into place. Another common example for sequential recommendation is repeated purchase, right? Let's say the person buy some products for the dog, for a pet anyway, and then some food, some medicine, and there's a recurrence pattern there, right? So sequential recommendation algorithms are able to capture that pattern, and they are commonly used for this task of reminding our users that to repurchase a product, which is an important source of revenue for e-commerce in particular. So inside sequential recommendation, there's a task, a more challenging task, that is this session-based recommendation. So basically, let's say you are browsing now for TVs for the World Cup, and then after 15 days or in the Black Friday, and after like a month later, 15 days later, you're browsing for smartphones for Christmas. So those sessions might be totally unrelated, because in e-commerce, for example, your context or your intent might make your path within that website very different. So in this case, it's more relevant to check what you're looking for in that session than looking too much in the past for other users' interactions to try to guess what the user might be interested for that session. And this can be observed by this plot here. This plot was generated from an e-commerce data set. So the y-axis here, I mean the height of the bars represent the similarity of two consecutive user sessions, right? So user has interacted in like in the previous slide, user had two consecutive user sessions. How similar are those sessions in terms of main category, category code, brand, and product, which are the colors here? And we can see that the longer the time between two consecutive sessions, like within 1 day, within 1 week, within 2 weeks, the longer the period, the less similar those sessions are, right? So this also helps to highlight the point that two user sessions, two sessions from the same user might be very different in terms of content. Another motivation for session-based recommendations is that some users might browse anonymously in many websites, right? And they might not accept the cookies. And in particular, with GDPR, past information about the user is very scarce these days. So many systems trust in session-based recommendation to consider only the interactions within the current session for recommendation. So yeah, let's talk a bit about Transformers4Rec library. And just to formalize, sequential session-based recommendation are about providing to a machine learning model, in this case a recommender model, a sequence of user interactions and the tasks to recommend what are the next items the user would like to either click or purchase. And the difference is that sequential recommendation leverages long sequence from past user interactions, for example, interactions in the last day or in the last month or in the last year. Yeah, it really depends on the information you have available for that user. While session-based recommendation only considers information of the current session. So I have been talking about Transformers4Rec. What is it about? So Transformers4Rec is an open source library that we have created at NVIDIA that targets this sequential and session-based recommendation problem. It's available for both PyTorch and TensorFlow, and we have an integration with the HuggingFace Transformers library, which is a very popular NLP library, and we try there to create a bridge between the NLP research and the RecSys, so that in theory you could use most of the transformer architectures available in the HuggingFace library with RecSys, which is great. So this is a work that was prepared and presented at RecSys conference this last year, with the most relevant, most important conference on recommender systems. And this piece is a part of our paper. So we did a survey and we observed that in the green blocks here are architectures that were proposed originally for NLP, for natural language processing or textual processing. And the blue ones are equivalent works or works that were inspired in the NLP work, which adapted some concepts from NLP into RecSys. And we see that there's a strong trend here of really leveraging NLP work on RecSys. So that was the inspiration for creating the NVIDIA Transformers4Rec library with this integration with the HuggingFace Transformers library. And yeah, it's really about taking the user interactions, as we said before, and leveraging a bunch of transformer architectures to recommend the next item. So you might not be aware of what's Transformer about. Transformer is not only the famous movie, but it's also a popular deep learning architecture that solves some issues we had before with some other sequential processing models like recurrent neural networks or RNNs. And transformers have been shown to be very powerful in NLP for language comprehension, comprehension, language modeling, and so forth. And it can also be used to process a user sequence and try to find really known obvious patterns there to recommend items for the users. So this is a diagram of a reference neural architecture that you can build with Transformers4Rec. So on the left here, you might have different types of input features. For example, you might have the item ID, which is a very important feature, right? Because we are talking here about the sequence of the clicked item. So the item ID is the most important one. You might also have some other categorical features. For example, what's the product category, the brand, or you might have some user features like what's the user gender or country. You might also have some continuous features like what's the product price, right? What's the user age? So all those features are combined in a sequence. And here in the bottom, we have with Transformers4Rec a module where those features are normalized and aggregated. And then we have some MLP layer here that combines all those features. And then, yeah, you're gonna have then a sequence of vectors where each vector represents the interaction, right? And then here we have the transformer block, which, as I said, a neural architecture component that's able to process a sequence. And it also outputs a sequence with hopefully, where hopefully we can have a good prediction of what's the next type, type of item the user would be interested on. And finally, you have in all the neurons, you usually have an output layer where we score all items here in this example and have a loss function to be able to learn this network, for example, cross entropy or some pairwise loss. But the idea here is really giving a sequence of interactions with all of those features, predicting which items the user could be interested next. So yeah, we support some of the HuggingFace Transformers architectures available in HuggingFace, like GPT-2, BERT, Transform XL, XLNet, Electra. We won't go into detail here, but you might read more online because they are very popular, and you might find many examples for them for NLP. So there are two concepts here. One is the architecture, the transformer architecture, and the other one is how they are trained, right? So we can train them like this. We have, for example, causal language modeling, where you provide a sequence of clicked items, like here, and you try to predict the next one, which is the 3, right? Item 3 is the next one. So you basically just use past information and try to predict the next item after the sequence. This is causal language modeling. This is how recurrent neural networks work, for example. And you can also train transformers like that. There's also the masked language modeling, where this comes from the BERT transformer architecture, where basically you mask some items in the sequence and you try to predict them using both the left context and the right context too. So that's how it works. There are also some more advanced options like permutation language modeling, where you permute the sequence as a way of data augmentation here to predict the next one. And there's the replacement language modeling, where it's very interesting because it uses it hides some items of the sequence and replaces them by some other items. And then the task of the discriminator network is to figure out whether that item is part of the original sequence or if it was replaced by our algorithm. And doing that, it learns to be very robust in terms of next item prediction. So this is more like an advanced topic, but just to give you a sense on how such networks are trained. And talking about Transformers4Rec, as I said, it was published as a paper in last year ACM RecSys conference. You might find the paper online for reading. And we also won 2 session-based recommendation competitions using these libraries. One was about a competition by Booking.com, and the task was predicting the next city of a multi-destination trip. So basically giving a number of hotel bookings the user has done, what's the next, for which city will be the next booking. And the other one was a more traditional example for next product prediction. It was promoted by Covell. So yeah, Transformers4Rec was a key library for winning those competitions. So yeah, we are pretty sure that it's very effective in terms of accuracy. And the good thing is that I have done some work to provide both TensorFlow and PyTorch API. And here we have some snippets. Ronay is going to share a more detailed example soon, but this is just to give you an idea that you can, from Transformers4Rec, you can either import our Torch module or TF module, And basically here, you just set the schema, which is a way to first to define for a given data set, what are the categorical features and what are their cardinality, right? Because we need to create the building and embedding table. And what are the continuous features? And then when we call this tabular sequence features, all embedding tables are created automatically and all MLP layers to combine those, those features. Then we create a prediction task, and we use a HuggingFace Transformer architecture, XLNet, and we just configure what's the dimension of the model, what's the number of heads and layers, and what's the total sequence length. And by doing so, we can take this configuration, turn it into either a PyTorch module or a TensorFlow module, which provides you some flexibility around which framework you'd like to work with. So moving to the last part of this conceptual slides, we not only provide Transformers4Rec, but we provide an end-to-end solution so that you can deploy such solution. For example, how a pipeline would look like for session-based recommendation. You would have a pre-processing step where you take your data where typically each row here is an interaction, and you want to group by the interactions by user for sequential recommendation or by a session for session-based recommendation. And it outputs two assets, the pre-processed data set in Parquet format and also a schema file which describes your data. As I said, what are the categorical and continuous features? Then we use that for training the model. And then in the end, you're able to deploy such model in a Triton Inference Server. And I'm going to talk about this a little bit soon. So just talk a bit NVTabular briefly. It's a way for you to do GPU accelerated preprocessing. And it's like a DSL on top of Rapids QDF, which is a GPU accelerated version of Pandas. But basically NVTabular provides you some very useful tools for preprocessing, and it's very, very fast. And basically you just create a DAG of operations, like for example, Spark does. And there are many feature engineering ops, for example, for normalizing continuous features or fitting missing values. And for categorical, the most important one is categorify, which converts, converts string or categorical values into contiguous item IDs so that we can create embedding tables from it. There's also, some targeting coding, and there are many, many options there. We highly encourage you to check it, not only for RecSys, but for any tabular data problem you have and massive data sets. I recommend it because it works with data that doesn't fit into either CPU or GPU memory, because it keeps loading data in a streaming fashion and applying those ops. So and regarding Triton, it's one of the popular choices on deploying machine learning models, and Triton is an NVIDIA product. It's not specific to burning. You can deploy any machine learning model there on CPU, on GPU. It can be something like an XGBoost model or some deep machine learning or some deep learning model. And there you have the ability to create an ensemble which connects multiple, multiple components. So here, for example, you can reuse the same preprocessing workflow you have used it for preparing data for training. You can reuse it here for inference, so that you don't have that train serving skill where you do some preprocessing for the model, but during inference, if you don't prepare features exactly the same way, the model will not be able to correctly predict what you're trying to predict. So we have the preprocessing workflow here being performed on the fly on a request. It can be an HTTP request or a gRPC request, and then the model is where Transformers4Rec live. The prediction here is what's the next item the user would like to access. So this was the conceptual part. Now I will move to Ronay so that she can show us some code and how all these pieces connect together in a practical example.
Thanks, Gabriel. Can I also get a share privilege? I need to, I think, yeah, awesome. I need to be able to, there we go, interesting. So do you see my screen? Do you see my Jupyter notebook?
Yes.
And if I switch to different tabs, do you see them as well?
Yes.
Okay, awesome. Thank you for confirming. So hi, everyone. My name is Ronay. I'm a senior data scientist at NVIDIA Merlin team. Thanks to Gabriel for this very nice presentation. So Gabriel talked to you about, particularly for the session-based recommendation systems and Transformers4Rec library. So he first talked about the theoretical background and the concept, and then he mentioned about how you can actually make it happen by using NVIDIA Merlin libraries. These are open source libraries. Anyone can just download them, use them. Our libraries work on both on CPU and GPU, so you can use them on different with different hardware and available resources. So I would like to I already shared with you 2 links. If you would like to know more about what is Merlin, we kept talking about NVIDIA Merlin. So NVIDIA Merlin, it's actually a suite of library framework. So it's a framework with many open source libraries, and it is particularly designed and built for high performing recommenders at scale. So I shared this link with you, and you can go and actually explore and learn more about each library. So what I'm going to show you, how we can actually create a session-based recommender model by using a data set, a publicly available data set, and train it. So with the Transformers4Rec library. So the data set I'm going to show you is available on Kaggle. It's called Huge's data set, and the data set does not have a lot of features. It has session ID column, timestamp, item ID, and category column. So as I said, this is just a demo. Okay, let me restart my kernel just to free my resources, my GPU memory. And I will start with NVTabular. So if you remember, Gabriel showed you a diagram how NVTabular, Transformers4Rec, and Triton is connected. I'm not going to give you an example about Triton today, but we have examples available on our GitHub repo. I'm going to talk to you how we can use NVTabular, which is a pre-processing, fast pre-processing and feature engineering library, how we can use NVTabular to actually manipulate our data, the raw data set, to create sequential features so that we can train a session-based recommender model. The first step is to actually create the sequential features. And we will do that with the NVTabular. We just import our required libraries. If you notice that we have QDF here, right? NVTabular actually is based on, built on top of it, on top of RecSys, NVIDIA RecSys QDF and DAS QDF. I believe you heard about them from Torren because he's one of the developers of the RecSys QDF library and DAS QDF, so he's very much involved in that. So I'm pretty sure you heard about that. So we just like read our data frame. That's it. And we call this data frame as an interactions data frame. At the very beginning, what we are doing is just some sort of data cleaning, like a classical data science practice. So we know that this data set might have repeated interactions. So imagine a session, right? You are on an online platform, and given in your session, let's say 30 minutes, we can call this as a session. Imagine in this session, you are clicking on the same item over and over, or there is some sort of like logging issues. So there are repeated interactions. So we just want to get rid of this. That's how we do that. And so we just clean the data set, and the first one is just showing you what does this data set look like. You don't have to save this. So this is our data set. We have session IDs. Look at that. So there's one session ID, and at this timestamp, in this session ID, user is interacted with this item ID, and it is category 0. And actually, we just created another time, another column here, which is a new feature, and it is called. It is created just to reveal the information about when the item was first seen. That's just another time, just a feature we wanted to create. So feature engineering, data cleaning is a common, as I said, common practice for data scientists. You can create whatever feature you want if you think it is meaningful, if you think it is going to reveal information, right, and make the model much stronger. So that's what we did. We just created an extra feature here, and let's just remove some of this unused data frames. Okay, now let's use NVTabular. I'm not going to go in detail about NVTabular, but we have, if you go to NVIDIA Merlin GitHub page, you can see that NVTabular is here. If you click on NVTabular, you can see a lot of examples about NVTabular. It's a fast pre-processing and feature engineering library. So NVTabular has, Gabriel mentioned that many operators, one of the very fundamental operator is to categorify, basically label and encode a given categorical feature. This is a very common practice. We do this with scikit-learn as well, right? We label encode and create like a continuous integer representations for a given categorical column. We don't do this for numerical columns, like for example, like price of an item or some other numerical columns, but we do this for the categorical columns. We use the categorify all. So what is going to happen here? We are basically taking some categorical columns and we categorify them. The important part here, I cannot go into every detail, but here the important part, we can create some custom actually feature. We can create features by using the Lambda app. So Lambda is like helping us to do some user-defined functions, which is very useful. We can even create our own custom operator and just run this operator. So what is happening in this cell is basically we are creating temporal features, like cyclical features by using sinus and cosinus functions. We don't have to. This is just an example that we want to create extra features. And we think these features are important and they are meaningful. But the most important thing in this actually here is, as I said, categorify operator, which is going to help us to create encode the categorical features. In the second cell, still the same NVTabular pipeline is continuing. Very important op called group by. Why we need group by? Because, as I said, you need to create per session ID, you need to create sequential features. That's how you will feed these sequential features to your transformer-based, session-based model. If you are familiar with RNNs or some other like sequence-to-sequence models, I think this will make more sense for you because you provide a sequence to the model. That's what is going to happen here. So NVTabular has an op called group by, which is you do the group by with pandas as well. The beautiful thing that it can help us to create list aggregations, and also we can do other aggregations together with this like sum, count, mean, and this is very actually useful for us. What is going to happen here? We also want to fix our session length, this sequence length per session. This is also very common practice in NLP. In NLP also, like we can fix the sequence length. So here we just want to fix it to 20. You can use it 200, whatever you want. If your sequence is less than this, you will be padding that. Padding meaning that you will like Generally padding happens with like 0. So you will make the sequence equal to the length of 20. That's why you need to do padding. If your sequence length is longer than 20, then you need to actually trim your sequence. So everything is happening actually here. All of the things I said happening here. We can slice, trim the sequence. We can pad the sequence. Everything can happen here. So that's why MTabler actually is very easy to use and very beneficial to use, because yeah, I mean, if you want to do this like in maybe different libraries, it might take longer in terms of lines of code, and also time-wise as well. This is running on GPU now, but as I said, you can do this on CPU as well. But running this on GPU giving you an advantage of running it very fast, right? Okay, so I just finished that, and this is just to avoid the warnings. And what am I going to do? Basically, I'm going to use my training set, interactions merge data frame, and I will fit this as we do with the scikit-learn, right? We do fit and transform. It's the exact same thing that is happening here. We are fitting this pipeline by using the statistics from the train set. Then we are transforming both train set and validational test set, whatever data sets we want to transform. That's what is going to happen. So we call this pipeline as a immutable workflow, and that's why we need to create an immutable workflow object here. And with the fit method, we can use our data set object, and then that's it. We can create our data frame. So this data frame, if you want, we can check. Let's check it. It is actually a QDF data frame, as I mentioned, right? So that's why we can get a QDF from here, because immutable is based on QDF and Dusk QDF. So this is what we are creating here. That's what we have. We, per every session, now we have sequential features. These are the features we are going to feed to our model. That's how our model will be trained, by using the sequential. Okay. Then now what we are doing here, we are doing some fancy stuff here. Basically, we just say there is a, pardon me, there's a day index column here. Can we actually group and save this data frame based on the day? So we are exporting based on the day. We can actually do that easily by using some utility functions, and we can do time-based split. So definitely, this is done very quickly. So what happened? That happened. I have now folders for the days. I just filtered these days as started these days from 178 to 182, basically last 5 days. And every day has its own train test and validation set saved as a Parquet file, a compressed file, which is much better than CSV files. So we created these folders. The reason we wanted to do this day split is just because we want to actually train our model with the daily. Basically, it's kind of like a sliding window approach. We want to train on the date 178 and validate on the 179. Then we will combine the data set first 2 days and validate on the 3rd day. So basically a sliding window approach. You don't have to do that. This is just an example how you can actually do this. So one concept that Gabriel mentioned, that how Immutable and Transformers4Rec are very much interacted with each other. This is actually done also by an object called schema. So we use a schema object, which is basically carrying all the information, metadata about our features. So what features? These are the process features, right? Remember, we generated these feature columns. So here, this is telling us some information about if these are categorical columns or not, if these are continuous columns or not, and what are the cardinalities, what is the sequence length, etc. So every this type of information can be actually stored in a schema file. Here you see a proto file, protobuf text file, but this schema file can be also just a simple text file as well. And we need a schema file because schema file is used for the model to actually extract this information, parse this information, and to be able to create the layers, that Gabriel showed you, the architecture, if you remember. So basically, with the schema, I can do many things. I can select what columns I would like to train my model. So imagine that you have, like, for example, item ID column, category about this item, product recency, meaning like how many days these products are, think about like age of this product, and like what is the temporal feature, like the day of week, right? This product is interacted with, etc. So basically, you can select whatever feature you would like to train this model on by select by name method. So schema has different methods. And this is one of them. So you might have 20 features created, but you might say, okay, I just want to train my model only with 3 features. And you can do that by just selecting the features by their names. So here's the magic happening. Gabriel has told you that Transformers4Rec built on top of famous HuggingFace Transformers library. It is inspired from the NLP architectures like GPT-2, maybe you heard about this, like BERT, right? And like XLNet, Transformer XL, etc. This example is showing how we can actually use XLNet architecture. It's a very famous architecture. It is actually strong architecture, and it gave very promising results in NLP domain. This is showing how we can actually use this architecture, leverage this architecture, not for an NLP problem, but particularly for a recommender system problem. What is the problem here? The problem here, given a sequence in a session, can you predict what is the next item that user is going to interact with? Or think about another problem. What is the next item that user is going to put in a basket, right? In a cart. So there are different use cases. Definitely you can use this architecture for. And this library as well, Transformers4Rec library. So what is the goal of the Transformers4Rec library? It is just to give users flexibility and easiness. Instead of writing this code by yourself with like really literally thousands of lines from scratch, we are trying to create high-level APIs so that users can take it just with a couple lines of code, customize it for their own use case, and just create results. That's the goal for us. So here we are creating our first bottom layer. Bottom layer is telling us how we can create our embedding layer, and how we can actually aggregate these embeddings, both for categorical columns and continuous columns. And also, this bottom layer is telling us what masking technique we will use. Shall we just use the causal language modeling that Gabriel showed you? Just take for example, a sequence and mask the last item, or can we actually mask randomly certain items in a sequence and use like bidirectional context, and predict this mask item? So that's what it is telling us, this masking parameter. And here we are using masked language modeling, basically meaning that we can do we use the bidirectional context. And here we are using XLNet configuration coming from HuggingFace. So, and our goal is to do next item prediction, and we actually create every block here, and then we glue them together in the last one. What is happening? We are creating a configuration for the transformer architecture, and we are gluing it with the bottom layer input module and the prediction task. That's what is happening here. These are all warnings, don't worry. And we need to set our training arguments, what data loader engine we are going to use, what is going to be the maximum sequence length and batch size, etc. Learning rate, are we going to do half precision, etc. And then we create our trainer class, which is very important because we are using HuggingFace trainer class with some modifications. And that's it. So we can train our model And this is going to do some sliding window approach. As I said, it's going to take the first day. See, it says launch training for day 178. It's going to train on 178, but it's going to evaluate on the 118. You don't have to do that way. This is the way that we want to do some incremental type of training and showing that capability that we can actually do it. So it's when it is going to finish, you see that we are getting some metrics. Very important metrics. One is NDCG. It's a very famous non-dominated cumulative gain. NDCG is a ranking metric, which is actually not only evaluating our, if for example, let's say at 20, if 20, let's say 20 estimated or 20 predicted items have the correct ground truth, it is also evaluating the ranking of this. So this is a very important metric. And recall is just basically, you know, the recall from maybe binary classification. It's basically gauging the quality of the model or evaluating the quality of the model based on if it is really having the ground truth or not. But the NDCG is very common, and technique, metric it's used, and you can see the NDCG 10, NDCG 20, basically 10 means like 10 items, 20 means the next 20 items. So you can see that 20 is always bigger than 10, or like 100 will be always bigger than 50, or because if you make the NDCG at K bigger, you will get a larger metric. The larger, the better, for sure. Same for the recall. So you can see that eventually we are getting the NDCG metric better. For example, in the last part, it's not getting higher. So that's it. That's end of my demo. But if you have any questions, I will be happy to answer. It might be too much to digest for a demo, but I know there are a lot of stuff going on. But in a nutshell, what I showed you today is like how you can use Merlin and Tabular to do pre-processing and to create sequential features. Why we need to create sequential features? Because the topic is session-based recommendation, which requires sequential features. And then I showed you how you can actually use Transformers4Rec to train an XLNet-based model. But this model is a recommender system model, basically to do next item prediction. So, and that's it. Actually, everything is, if I run this notebook end to end, it just runs like in less than a minute or something, or maximum 2 minutes. It's pretty fast actually. And this was running on, as I said, on a single GPU on my workstation. Yeah, but you can run this on CPU as well. Yeah, that's pretty much it is from my side. If I can stop sharing, I'm happy to answer the questions.